Welcome to Summarize Science. Today we are looking at a major breakthrough in how large language models, or LLMs, tackle complex mathematical problems. Most of us are familiar with chain-of-thought reasoning, where an AI explains its work step by step. However, researchers found a structural flaw in this approach. AI often starts calculating before it truly understands the nature of the problem. They identified a paradigm-level gap between knowing what to solve and how to solve it. Imagine trying to fix a car engine by grabbing a random wrench before you even know if the issue is the battery or the fuel line. To bridge this gap, the researchers proposed a new framework called PPC, which stands for Preplan. This adds an explicit pre-plan stage where the AI must identify the problem type, useful tools, and potential pitfalls. On page 2, we can see a clear comparison of how this works in practice. In the top example, a standard AI commits to a difficult and fragile calculation route and eventually gets the answer wrong. In the bottom example, the new pre-plan stage recognizes the problem's specific form and suggests a much safer shortcut. By identifying the right strategy first, the AI's final count is correct and much more reliable. One of the biggest challenges the researchers faced was ensuring the AI didn't cheat by doing the math during the pre-plan. To prevent this, they developed a spoiler score filter to catch any pre-plans that revealed the answer or performed derivations too early. They also used a method called reinforcement learning to reward the AI when its plan strictly followed its pre-plan. This ensures that the initial analysis is actually being used as a roadmap for the entire solution. The effectiveness of this method was tested across 4 different model families and 5 major math benchmarks. The results, highlighted on page 6, show that PPC achieved the best results on 39 out of the 40 metrics tested. It significantly outperformed existing methods that either didn't plan or used a more basic planning style. This shows that a little bit of high-level meta-thinking goes a very long way in difficult subjects. You might think that adding an extra stage would make the AI slower or more expensive to run, but that isn't the case. As shown in Table 5 on page 8, the PPC method actually used fewer tokens than standard reasoning in several tests. By committing to a clear plan early on, the AI avoided the redundant detours and rambling that often happen in standard models. It proves that clear thinking leads to more concise and efficient communication. The researchers also ran a faithfulness test to see if the AI was actually paying attention to its own pre-plan. When they purposefully gave the AI a mismatched pre-plan from a different problem, the model's accuracy collapsed. This confirms that the AI is genuinely relying on its initial strategic analysis to guide its work, rather than just ignoring it. If the pre-plan was just fluff, the AI would have been able to ignore the wrong instructions and still solve the math. To recap, the researchers found that understanding is a distinct stage that must happen before solving. By forcing AI to analyze problem types and constraints first, they have created a much more robust mathematical thinker. This shift could mean a future where AI is significantly more reliable at handling high-stakes technical tasks. The pre-plan approach might eventually be used for coding, law, or any field requiring deep strategic thought. It's a big step toward AI that doesn't just guess, but truly understands the task at hand. Thanks for watching Summarize Science, and stay tuned for more deep dives into the world of AI research.